Yesterday, we learned to add. In grade 1, you learned to add, but you learned to add scalars in grade 1. 2 plus 3 was equal to 5. 3 plus 4 was equal to 7. In grade 6, you learned to add. You learned to add vectors in grade 6, vectors in one dimension, but in different directions. So in other words, maybe you had a north, maybe you had a south. 3 plus 4 might have equaled 7 then, but it might have also equaled 1 or minus 1, depending upon the directions of the 3 and the 4. If one was to the north, one was to the south. Yesterday, we learned how to add 3 plus 4 when it was to the east and north, or to the south and west, as opposed to in one dimensions. It was what we call non-collinear vectors, or vectors that are in 2 dimensions. 3 plus 4 can still equal 7 if they're in the same direction. They can still equal 1 or minus 1 if they're in opposite directions. But 3 plus 4 can equal 5 or some other number if we've got a 2-dimensional problem now, where we're trying to add these vectors in 2 dimensions. Remember we said yesterday, the overriding goal, the life goal of vector addition is to get to a right-angled triangle. Okay, because we know how to deal with the right-angled triangle. It's not as easy as saying 3 plus minus 4 is minus 1. Not as easy as that, but it's a lot easier than dealing with 3 plus 4 equals 7, or 3 plus 4 is equal to 5, and just kind of doing that in your head. Get a right-angled triangle, a vector diagram that is a right-angled triangle, and then use some trigonometry that we used yesterday. Pythagorean theorem and the inverse tan function. Big rule that I want to emphasize here, that I want to highlight again when we're drawing those vector diagrams, front to back. Okay, remember when we're drawing 2 vectors, got to draw them front to back. Let's say we've got one to the east that's 10 meters. We got another one that's to the south at, let's say, 9 meters. There's a couple of options that we can draw these, but there's 2 options that don't work. Okay, 2 options that are correct, 2 options that are incorrect. I'm going to draw 4 different possibilities here, and I want you to tell me which one or ones are correct here, okay? So let's draw the first one. Running out of space here. The 4th one's going to be up here. Okay, so we got options A, B, C, and D. Okay, is A a correct option? Can I draw it that way? Is A a good vector diagram? Sure it is. Why? How do you know it's a good vector diagram? How do you know that this works? Yep. Good. It's drawn front to back. The front of the 10 is drawn to the back of the 9. Good. Is B correct? B, no? Why not? Good. You can't draw it back to back. You can never draw those lines, those component vectors back to back. What about C? Does that one work? Right. You can't draw it front to front either. So B and C are against the rules here. What about option D? Is that good? Is that one good? Yes, it is. How come? It's, yeah, back to front. Doesn't matter how you say it, because it is, usually we say it's drawn front to back, but it's also drawn back to front, right? So that's okay. As long as you remember that the front has to go with the back, whichever order you say it, it doesn't matter. All right, so those 2 are good. Now let's draw the resultant vector, which is the sum of the vectors, the sum of both of those vectors here, the total of them. The first resultant vector goes right here. The second resultant vector goes right here. Now, where does the arrow go? Does the arrow go at end 1 or end 2? End 1 or end 2? It goes at end 2, yeah. It's kind of the opposite to the rules of the other vectors, right? We're going to draw that back to front. We're going to draw that from start to the finish. And in the end, when we find that value, the direction we had it drawn doesn't really matter. But when we go to find the direction a little bit later on today, it will matter. So it's important, even though yesterday you would have gotten the correct answer by drawing it in the wrong direction, today you won't get the correct answer if you draw it in the wrong direction. What about this one over here? Position 1 or position 2? 1 or 2? Sam? Position 2. Good. Now, it seems to me when we find those two resultant vectors, okay, in diagram A and diagram D, aren't we going to get the same value there? Square root of 10 squared plus 9 squared, isn't that the same as the square root of 9 squared plus 10 squared? Do we get the same value? Of course we do. Of course we should get the same value, because in the end, we can add vectors together in any order we want, just like we can add scalars together in any order we want. 9 plus 10 is the same as 10 plus 9, whether we're talking about scalars or whether we're talking about vectors. We should get the same answer. Good? Well, what do we do if we had more than two vectors? If we had a 10 to the east and a 9 to the south, we can draw it like diagram A or diagram D. But what do we do if we had a situation like this, where maybe we had 10 to the east, we had 5 to the north, we had 10 to the south, we had 15 to the west, and then maybe we had another 5 to the north. What do we do with those? Well, let's draw our diagram and see what it looks like first, okay? We had 10 to the east, then we had 5 to the north, then we had 10 to the south, then we had 15 to the west, and we had 5 to the north. Oh boy, that's kind of ugly. We can draw a resultant vector in there though, right? From start to finish. By the way, are those vectors drawn correctly? Front to back? Every single one of them is drawn front to back. They're all correct. So let's draw a resultant vector that goes from start to finish right here. Now, how do we find the value of that resultant vector? Let's break it up into our x's and y's. The first vector, the 5, how much of that is x? Sorry, the first one is the 10, right? How much of that 10 is x component, Tyler? 10, good. How much of that 10 is y component, Tyler? Good. How much of that 5 is x component, Leah? Good. How much of that 5 is y component? Good. How much of that 10 is x component? Peyton? Good. How much of that 10 is y component? Almost. Good. How much of that 15 is x component? Yep. Good. Negative 15. Julia, how much of that 15 is y component? Good. And finally, how much of that 5 is x component? I think you're ready to raise your hand up there. 0. How much of that 5 is y component? Good. So let's add these up. 10 plus negative 15 is negative 5. 5, negative 10. Oh, that didn't work out so well, did it? That's okay. What do those add up to give me? 0, right? What would we normally do at this point? What would we normally do at this point? Well, we'd normally draw a right-angled triangle, right? We draw our x component, we draw our y component, and then we combine them using the Pythagorean theorem. What do we do at this point? Yeah, you still could kind of do that, but you don't need to, because in the end, if there's an x component of -5 and a y component of 0, what's the answer? The total is 5 to the left. Right? Does that make sense? So I didn't draw this quite correctly. That should have went up to there, and then my resultant vector goes right there. Okay, in the end, I don't need to do the vector diagram triangle for this one because my y component is 0. If it wasn't, draw the triangle. If it is, then it's just your x component. All right, we had a couple questions for homework. They were on that worksheet, questions 4 and 5 on the worksheet. Let's pull those out now if you don't have them out. Question 4. We'll go at it here, whether you think you've got the right answer or not. We'll go at it as a group here to make sure that you've got the right answer here, okay? We got a vector diagram drawn already with the exception of a resultant vector. I'm going to draw the resultant vector from start to finish here in red. And then I'm going to ask you which way to put the arrow. Do I put the arrow at position 1 or position 2? Position 1 or 2? Joseph? Position 2. Always goes from the start to the finish, right? Now, some of you might look at this and say, oh, I can do 2 triangles here. No, you don't want to go there. Okay, you don't want to go there because you don't know what the length of this triangle, this side of the triangle would be, or the length of this side. You don't want to go there. So what we're going to do here is break this up into x's and y's, just like we did a minute ago. X's and y's. The x component of the first one is 10. The y component of the first one is? How much of that 10 is y component? 0. Second one, x component, 5 meters. Jeremy? Good. The y component is? Good. Third one, x component of the 15. Hey, what's the x component of that 15? Good. And what's the y component of that 15? 0. Let's add these up now. 10 plus 15 is 25. 0 plus 5 plus 0 is 5. Let's redraw it. We got 25 to the right, and we got 5 upwards here. The resultant vector is drawn from start to finish. Let's find the value of that resultant vector. It's the square root of 25 squared plus 5 squared. That's going to be the square root of 650, which is going to give you, I don't know, 26, something like that. 25.49. Is that okay? How many people got that 25.49? Good. Okay, let's take a look at the other one now, number 5. A little bit harder. We can draw a resultant vector still from start to finish. Can you tell me where the arrow goes? Position 1 or position 2? 1 or 2? Position 1, position 2. No? Position 1? Yes. It goes from start to finish. Okay. Notice I switched it, the order that I said that. Usually it's position 2. Okay, I switched the order of them, position 1 and 2, just to see if you're remembering whether it's position 2 or you're remembering exactly where you're supposed to put it. You passed. Good. All right, let's do the x and y components now like we have for the other questions. How much of the x component, how much of that 8 meters is x component? Yeah. How much of it's y component? Good. 12 meters is how much x? How much of that is x component? 12, yeah. How much is y component? 0. 10 meters. And 10 meters, positive 10. How much of this is x? Yep. Good. And 0, good. Let's add these up. 12 plus negative 4 is 8. This is 2. So we've got 8 and a 2. Let's draw it this way. 8 and 2. The resultant vector is right here. Did you look at that? The resultant vector, when I draw it as a 2-vector diagram, looks the same as the resultant vector when I draw it as a 4-vector diagram. Let's find the value of that. It's 8 squared plus 2 squared. That's square root of 68. I don't know, I'm going to say 8.5, 8.24. Guys feel okay with that? Yeah? Good. All right. What happens if I have a vector that's at a funny angle? Like what happens if I don't have a vector like this, where I'm trying to find the x and y components? What if I have a vector like this? Well, before we do that, let's just make sure that we can find the x and y components when we've got straight vectors like this. Okay, once again, real quick review here. What's the x component of this 10 meters? 10. The y component is 0. The x component of this one is? Tegan, what's the x component of that 200? How much of that is horizontal? Sorry? Good. And how much of its y component? Good. How much of this is x component? Okay, how much of that is x component? Good. And how much of its y component? Good. And finally, this last one, how much of that is x component? Ilma? 0. And how much of its y component? Good. Negative 35 or minus 35. We're good with that, right? Even though not everyone's raising their hand and volunteering here, I think everybody's good with that. I hope. Please let me know if you're not. But what if you have a situation like this? How do you deal with that exactly? Right, we can find the x and y components of a simple vector that's going to the right or going to the left or up or down. But how do you find the x and the y components of this? What I want to do here is draw a little triangle. Now remember, this isn't the triangle that is the vector diagram that's allowing me to find the hypotenuse. Okay, that's not it. This is another triangle that I'm creating to find the x and the y components of one of the vectors. This is part of getting us to the end of finding the sum of all the vectors. Only part of it. Okay, it's finding the components of the vector. Remember, we had to find the components of each of these vectors. We have to find the components of each of these vectors as well. How do we do it? Well, let's draw a triangle here around it. I usually draw that triangle with dotted lines, but you don't have to. That triangle should go around the angle. So here I've got it drawn underneath the line. I could draw right here. No, that wouldn't work because that doesn't go around the angle. So the triangle needs to go right here. Now that triangle will always be a right-angled triangle. That's good news because it allows us to use the basic trigonometry functions sine, cos, and tan. Before we go any further, let's make sure that you remember those or you understand those. You guys did trigonometry, I think, in grade 9 for the first time, sine, cos, and tan. You guys remember what sine is? The sine function is good, opposite of hypotenuse. So sine theta, okay, sine theta, the angle, is equal to opposite. That's the sine that's opposite, or the side of the triangle that's opposite the angle, divided by the hypotenuse. And the hypotenuse is the longest side. Cosine is, yep, the adjacent over the hypotenuse. Now, the adjacent side of the triangle is the side that's touching the angle, but is not the longest side. So, for instance, in this question right here, the opposite would be this one, because it's opposite the angle. The adjacent, well, both of these are touching the angle, but this is the longest one, so it's the hypotenuse. So this has got to be the adjacent. Okay? Cosine is adjacent over hypotenuse. Finally, tan theta is equal to, yep, opposite over adjacent. Good. So that's the side that's across from the angle right here. Okay, in this case, it would be right here, divided by the adjacent side, which is the side that's touching the angle, but not the longest side. Okay, opposite over adjacent. Now, how do you remember those trig functions? Yep. SOHCAHTOA, right. You learn probably in grade 9 or grade 8 or whenever it is that you learn this stuff for the first time, that little mnemonic device, SOHCAHTOA. So, S-O-H, Ka, C-A-H, Toa, T-O-A. Sine, cosine, and tangent. Now, we're going to use one or more of these trig functions to find how much of that 100 meters is x component and how much of that 100 meters is y component. What variable do we have in that triangle given to us already? Is it opposite, adjacent, or hypotenuse? It's the hypotenuse. Okay, so we're not going to use tan because tan doesn't have hypotenuse in it, right? We're going to use either sine or cosine. If we're trying to find the x side here, you guys okay? If you're trying to find the x side, which side of the triangle are we looking for? Opposite or adjacent? Again, it's not hypotenuse, because the hypotenuse is, we've already established, is 100. Which side are we looking for x? Opposite or adjacent? Julia? It's the adjacent side. It's the side that's touching the angle, but not the longest side. So it's adjacent. If we're looking for adjacent, we've got hypotenuse. Which trig function do you think we're going to use? Okay. Cosine. Let's say cosine 30 degrees is equal to adjacent, which is x, over the hypotenuse, which is 100. Now the 100 goes up by multiplying. 100 times cosine 30 is 86.6 meters. And the y component, well, it's the opposite side. Let's use the trig function sine. Sine 30 degrees is equal to opposite over hypotenuse. 100 goes up by multiplying. Y is equal to 50 meters. So really what we've done here is turned that 100 meters into 86.6 meters and 50 meters. Hey, we know how to deal with both of those, right? We spent yesterday dealing with those two vectors. All we've done here today is turned this funny angle vector into two vectors that we know what to do with. I want you to remember 5 words whenever you see an angle like 30 degrees. Okay, whenever you see an angle that's not 0 or 90 or 180 or 360. Okay, 5 words. Repeat after me. I don't like funny angles. Okay, say it again. You say it now once here, because you guys are smart enough to remember this, right? I don't like funny angles. So what do? We get rid of them. We don't like funny angles, we get rid of them. And we get rid of them by doing what we just did right here. Yep. Let's take a look at the second example there. What do you see there that kind of strikes you? Oh, an angle. It's not 0 or 90 or 180 or 360. What do we think kind of in our minds? I don't like funny angles. So what do we do with it? We get rid of it. Let's label this as x and this is y. Which side of the triangle this time is x? Which side of the triangle is x? Joseph? This is opposite this time, right? We've got hypotenuse. We're looking for opposite. Which trig function are we going to use to find the x component? Yep, sine. Last time it was cos. This time it's sine. Depends on where the angle is. Sine 30 degrees is equal to opposite over hypotenuse. X ends up being equal to 17.32, I think. Let's say cosine 30 degrees is equal to adjacent over hypotenuse. No, that's not right. That should be 10, shouldn't it? Cosine 30 degrees is equal to adjacent over hypotenuse. The y component, or the adjacent side, ends up being equal to 17.32 meters. So what I've effectively done here now is replace this 20 meters at 30 degrees, which I don't like because it's a funny angle. I've replaced it with this. Oh, wait. That should be negative, shouldn't it? Because it's downward. I've replaced it with this one and this one. I know what to do with that. We did that yesterday. We checked over a couple homework questions with that today. We know what to do with the 10 and the 17. We didn't know what to do with the 20. Now we do. All right. See a couple pens moving, so I'll wait for a second here. Let's do one more example here before we set you free on a few worksheet questions here, okay? We got a 60-degree angle. We got a vector that's 100 meters long, and it's going south and west or down and to the left. Okay. That's part of a bigger picture. Let's say that we had 4 vectors that we had to add together. This is only one of the vectors. But to do that, to add them together, we need to know what the x and the y component are for each of them. So let's get the x and the y component for this 100. Let's complete the triangle right here. That doesn't work because that triangle isn't surrounding the angle. I don't want that triangle. I want this triangle, the triangle that goes around the angle. Of course, this angle is going to be 90 degrees. That's good because it allows us to use sine, cos, and tan. The 100 meters, is that opposite, adjacent, or hypotenuse? Nathan, is that opposite, adjacent, or hypotenuse? It's hypotenuse, right. Okay, so we're going to use either sine or cosine because they're the only ones with hypotenuse in there. Is the x component opposite or adjacent? Yep, it's adjacent. So if we're looking for adjacent, we've got hypotenuse. Let's use which trig function? Question? No? X is adjacent here because it's touching the angle, right? The side that's touching the angle is the adjacent side. Okay, this y component isn't touching the angle, so it's the opposite side. Now, we actually have two sides that are touching the angle, the x and the 100 meters. How do we know which one's adjacent? How do we know which one's hypotenuse? Well, the hypotenuse is the longest one, and the adjacent one is the one that's left over. Okay? No. I keep thinking you're starting to raise your hand there and ask a question. So we're looking for adjacent. We've got hypotenuse. Julia? Let's use the cosine function, right? Cosine 60 degrees is equal to adjacent over hypotenuse. That ends up being 50 meters, I believe. Sine 60 degrees is equal to opposite over hypotenuse. And the y component works out to be 86.6. So what I've effectively done, this funny angle that we see right there that we don't like because we don't like funny angles gets replaced with this. I'm going to leave that up there actually so you can see this a bit better. Gets replaced with this. I've got 50 to the left, right? 50 to the left because that went to the left, and 86.6 downwards. Guys, we know what to do with these vectors. They're just straight regular vectors. Now we just have two of them instead of one. The 100 meters became a 50 and an 86. But I'd rather deal with two of them like that than one of them that's at 60 degrees. All right, what I'd like you to do right now, once you have that copied out, as long as you understand this, that is. Okay, if you don't, then ask questions right now, please. If you do, then I'd like you to take a look at questions 6 to 13 on your worksheet. Some of these are real straightforward ones, 6, 7, and 8, and then 9, 10, 11, and 12, and 13 are a little bit more like this. I'll give you a few minutes to work on those questions now. Okay, guys, taking a look at 10 and 12 here. 10, we got a 60-degree angle here, and it's 50 meters. The magnitude of the vector is 50 meters. We're trying to find these components so that in the end we can add vectors together here. Let's draw the triangle this way, around the angle. This would be our x component, this would be our y component. Now, which side of the triangle is the 50 meters? Which side of the triangle is the 50 meters? The hypotenuse, good. The vector you have will almost always be the hypotenuse. Almost always. Not necessarily always, but almost always. So we've got the hypotenuse. We want to find the x side. Is the x side the opposite or the adjacent side, Bree? The x side right here, opposite or adjacent? Yes, because it's not connected to that 60 degrees, right? It's not touching the 60 degrees, so it's opposite. Listen, if we're trying to find the opposite side, we've got the hypotenuse. Which trig function do we want to use? Good. So we're going to say sine 60 degrees is equal to x over 50. That's going to give me 43.3 meters. Now, for the y component, obviously, we're looking for the adjacent side. That's going to be the cosine function. Cosine 60 degrees is equal to y, or adjacent over hypotenuse, and y is going to end up being equal to 25 meters. Good? One thing you'll have noticed, guys, with all the examples that I've given you so far, we're either dealing with an angle of 30 degrees or 60 degrees. That's not necessarily going to be the case on a test, right? So why am I dealing with 30 degrees and 60 degrees in the examples that I'm giving you? Why 30 and 60 in the examples? Because they're easy. They're easy to do in my head. Cosine 60, cosine 30, sine 30, or sine 60, cosine 30, whatever I said. Okay, all those different possibilities, right? We can do those in our head. Okay. If you can't do it in your head, just do it in your calculator. Cosine 30 on your calculator, right? It's no different than saying cosine 26. Just that I can't do cosine 26 in my head, and I can do cosine 30. So don't get too used to the 30 degrees and the 60 degrees. The other questions work exactly the same. They just won't be quite so convenient, that's all. All right, question number 12. We got a 30-degree angle here. Let's draw our triangle around the 30-degree angle. The x side of the triangle is the opposite or adjacent side. Victoria, opposite or adjacent side for x here? Yes, good. So if it's the adjacent side and I've got the hypotenuse, then what am I going to use? Adjacent and hypotenuse. Ah, adjacent and hypotenuse. Ah. Opposite and hypotenuse would be O. Adjacent hypotenuse is ah. So ka. Toa. Which trig function is it? I'll just say it because that didn't make a lot of sense to you, did it? Or anybody else probably for that matter. All right, cosine 30 degrees because it's the adjacent side that I'm looking for given the hypotenuse. Cosine is equal to adjacent over hypotenuse. That's going to be equal to, is it 34.6 something? 34.6 meters. And the y component here, using the sine function, because it's the opposite side, that's exactly 20 meters. Good? How many people got that for number 12? Good. Now, one thing to remember, when you were going to add vectors together, okay, we have to make sure that we make the x component a positive because it's to the right. The y component would be a negative because it's downward. Right? You guys feel good with that? You're just about ready to tackle 14, 15, and 16 on that worksheet then, almost. Let's try adding these vectors together now. 25 meters, 20 meters, 15 meters, 20 meters, and 5 meters at an angle of 30 degrees. The first thing we do when we see this, say to ourselves 5 words. I don't like funny angles. So we get rid of it. Let's take that 5 meters at 30 degrees. Pay real close attention here, okay, guys? Take that 5 meters, put it over here, and break it up into x's and y's. X is the adjacent side, so we're going to say cosine 30 degrees is equal to adjacent over hypotenuse. X ends up being equal to 4.33. Sine 30 degrees is equal to opposite over hypotenuse, or y over 5. Y is equal to 2.5 meters. Now, watch what I'm going to do. I'm going to physically erase this 5 meter vector and replace it with a 4.33 meter vector and a 2.5 meter vector. Doesn't this question look easier now that I don't have that 30-degree angle? But all I've done is broken that 5 meters at 30 degrees up into 4.33 and 2.5. Now I can analyze it the way that I did the questions for homework last night. Now let's go x's and y's. 25 for the x, 0 for the y. 0 for the x, negative 20 for the y. negative 15 for the x, 0 for the y. Negative 0 for the x, negative 20 for the y. 4.33 for the x, and 0 for the y. 0 for the x, and 2.5 for the y. Can you see what I've done there? I've changed the question from a 30-degree funny angle question to a straight across, straight up question. 25 plus negative 15 is 10, plus 4.33 is 14.33. Negative 40, negative 37.5. I've got 14.33. I've got 37.5. We know what to do with this. Do the Pythagorean theorem like we have for probably 5 or 6 questions thus far. Is that okay? All right. What I'd like you to do now, please, is questions 14, 15, and 16 on that worksheet. Remember, we're still only finding the magnitude. There is a direction. We're still only finding the magnitude. Once we've got that nailed for all these types of questions that you see on the worksheet, then we'll worry about the direction. Okay? All right, guys, we're going to take a look at question number 15 as a group here. Okay? 15, I've had a couple of questions on already, and I can see where the problem lies. So everybody look up here, please. All right, we got one funny angle in question 15. That's good compared to, say, 16, where we have 2 funny angles, but that's okay. 2 funny angles just means a little bit more work, that's all. I don't like funny angles, so I want to get rid of that 30 degrees. Let's draw it off to the side. Okay, just the 5 meters at 30 degrees. Okay, here we go. There's 5 meters. There's my 30-degree angle. There's my x. There's my y. What you don't want to get caught up in doing is saying, oh, look, the x is 8. No, it's not. The x is 8 for the second vector. That's independent of the third vector. How much of that 5 is x component? Not 8 of it. You can't have 8 of a vector that's only 5 long. It's got to be a number that's smaller than 5, right? So let's figure that out. It's the adjacent side and the hypotenuse. So let's say cosine 30 degrees is equal to adjacent over hypotenuse. That ends up being 4.33. The y component is the opposite side. So let's say sine 30 degrees is equal to opposite over hypotenuse. Y ends up being equal to 2.5 meters. So here's what I've done. I've gone off to the side with that 5 meters at 30 degrees. I found the x component. I found the y component. I'm going to redraw this whole diagram. I got 5 meters down. I've got 8 meters across. I've got 2.5 meters down. How do we know it's down? Look at the original diagram. You end up, for this 5 meters, you end up below where you started at the beginning of that 5 meters. It's down. And we have 4.3 meters to the left. There. So I've just changed that 3-vector diagram with a funny angle into a 4-vector diagram with no funny angles. Now let's do the math on this one, the x and the y components. For the first one, x is 0, negative 5, 8, 0, 0, negative 2.5, and negative 4.33, and 0. Add these up. Negative 12.33. Add these up. Negative 7.5. Combine them. We've got negative 12, negative 7.5. Here's the resultant vector. We can find that, right? It's the Pythagorean theorem. Yep. Oh, yeah. Yeah. No, you're right. 8 plus negative 4 is not negative 12, right? So what does that equal? 3.67. So that should be a positive value, right? So it should be 3.67 to the right and 7.5 down, which makes sense, actually, if you look back to your original diagram, because your original diagram, the resultant vector went down and to the right. It should go down and to the right in my new diagram as well. Is that okay? Now, I had a couple people ask me about this. Said, Could I change that angle, 30 degrees, into a triangle, an angle that looked like this? With 60 degrees? Could I do that? Sure you could. If you use sine for x here, okay, sine 60 is equal to opposite over 5, then what are you going to get for the value of x? 4.33. Just the same as you did the way that I did it. So it doesn't matter which angle you use as long as it's a correct angle. How many people are finished that sheet now? Okay, we've got about 4 minutes left. Keep working on it if you're not. If you are finished and you're comfortable with it, great. Put your stuff away, you're done.